Welcome to our deep dive into some climate research you sent our way about a potential tipping point in the AMOC.
The Atlantic Meridional Overturning Circulation.
Right, the AMOC.
Yeah.
It's a huge system of ocean currents, and this research published in Science Advances suggests it might be in trouble.
The AMOC acts like a massive conveyor belt transporting warm surface water from the tropics northward.
Keeping Europe relatively mild.
Exactly, as that warm water flows north, it cools, becomes denser, and eventually sinks in the North Atlantic. Then it flows back south at depth, completing the cycle.
It's a delicate balance, and this research suggests it could be disrupted.
The study focused on freshwater forcing as a potential trigger for an AMOC collapse.
Freshwater forcing.
Yes, increased freshwater input from melting glaciers and changes in precipitation patterns can disrupt the delicate balance of salinity and temperature that drives the AMOC.
So it's like adding fresh water to a saltwater tank and throwing off the equilibrium.
Precisely, and this disruption could have severe consequences for global climate patterns.
The study used a climate model called the Community Earth System Model, or CESM, to simulate how the AMC responds to increasing freshwater forcing.
The model showed a gradual weakening of the AMOC over time, and then a sudden collapse after about 1750 years.
A collapse of the AMOC that sounds pretty catastrophic. What would that look like in the real world?
The impacts would be significant and widespread. Europe would experience a dramatic cooling.
How dramatic are we talking about?
Some cities could see temperature drops of 5 to 15 degrees Celsius.
Wow, that would make London feel like it's on the same latitude as Canada.
Exactly. The climate would shift drastically, impacting agriculture, infrastructure, and daily life.
And it's not just Europe that would be affected, right?
The AMOC influences global weather patterns, including the Intertropical Convergence Zone, which dictates rainfall in crucial regions like the Amazon.
So a weakened AMOC could disrupt rainfall patterns, leading to droughts or floods in different parts of the world.
Precisely. The Amazon rainforest, for instance, could experience reduced rainfall, potentially transforming it into a drier savanna ecosystem.
That would be devastating for biodiversity and the Amazon's role as a carbon sink.
Absolutely. The implications of an AMOC collapse are far-reaching, and we're only beginning to grasp the full extent of the potential consequences.
This research highlights the urgent need to understand and address the factors that could push the AMOC towards a tipping point.
It's a wake-up call to the global community that we need to take swift action to mitigate climate change and protect this vital component of our planet's climate system.
The fate of the AMOC is intricately linked to our own, and this research underscores the need for continued research monitoring and international collaboration to address the challenges posed by climate change.
The time to act is now before we reach a point of no return. We've touched on the idea of a tipping point for the AMOC, but let's dig a little deeper into what that actually means.
It's this threshold beyond which a system undergoes a rapid and often irreversible change. And this new research suggests the AMOC might be approaching such a threshold.
Exactly, and the CESM simulations provide valuable insights into how this tipping point might unfold.
The study mentions a gradual weakening of the AMOC followed by an abrupt collapse. Can you elaborate on what the model showed?
The simulations gradually increased the amount of freshwater flowing into the North Atlantic over a period of 1,750 years, mimicking the effects of melting glaciers and altered precipitation patterns.
And how did the AMOC respond to this influx of freshwater?
Initially, the AMOC strength, which is measured in sverdrups, declined slowly. A sverdrup represents a volume of water transported per second about 1 million cubic meters.
So kind of like a giant underwater river.
Exactly. At the start of the simulation, that AMOC was transporting about 10 sverdrups of water, but as freshwater input increased, the AMOC strength gradually diminished.
And then after 1,750 years of this gradual weakening, the model showed a sudden collapse.
Precisely, the AMOC strength plummeted to near zero, indicating a near-total shutdown of this massive ocean current system.
What happened to global temperatures in the simulation after the AMOC collapsed?
The model showed a distinct temperature pattern after the collapse. The northern hemisphere experienced significant cooling, especially in the North Atlantic region.
So Europe got colder as that heat transport from the tropics shut down.
Exactly. Meanwhile, the southern hemisphere saw a corresponding increase in temperatures, creating a kind of seesaw effect.
So the AMOC acts as a global thermostat, regulating temperatures between the hemispheres. Its collapse would disrupt that balance, leading to these regional shifts in temperature.
Precisely, and the impacts extend beyond just temperature changes. The study also looked at how the AMOC collapse affected the Intertropical Convergence Zone, or ITCZ.
The ITCZ plays a crucial role in global rainfall patterns, right?
Yes, it's a band of low pressure near the equator where trade winds converge, bringing moisture and precipitation.
So how did the AMOC collapse affect the ITCZ in the model?
The simulations showed that as the AMOC weakened, the ITCZ shifted southward. This shift altered rainfall patterns across the globe.
So some regions might get wetter while others become drier.
Exactly, and these changes in precipitation could have cascading effects on ecosystems, agriculture, and human societies.
The study also highlighted changes in sea ice coverage after the AMOC collapse.
Yes. With the reduced northward heat transport, the Arctic region experienced a significant expansion of sea ice, amplifying the cooling effect in the northern hemisphere.
So more ice means more sunlight reflected back into space, further cooling the planet.
Exactly. It's a positive feedback loop known as the ice-albedo feedback.
So the AMOC collapse triggers a chain reaction, impacting temperatures, rainfall, and even sea ice coverage. These simulations paint a rather grim picture of the potential consequences.
Indeed, they underscore the importance of understanding the factors influencing AMOC stability and taking steps to mitigate the risk.
But the study also went beyond simulations and looked at real-world data to assess the current state of the AMOC.
Yes, the researchers used a combination of observational data and climate models, known as reanalysis products, to study the historical behavior of the AMOC.
And they focused on a specific indicator called FAVES, which you mentioned earlier.
Precisely. FAVES stands for the minimum of the AMOC-induced freshwater transport at 34 degrees south in the Atlantic. It's a measure of the salt advection feedback, which is crucial for maintaining AMOC stability.
So like a pressure gauge for the AMOC. If FAVES is declining, it suggests the system is becoming less stable and more susceptible to collapse.
Exactly. And the reanalysis data showed a concerning trend. FAVES has been steadily declining over the past 40 years.
So this real-world data seems to support the model's projections of a weakening AOC.
Yes, and the observed trend in FAVES is consistent with projections from the latest generation of climate models known as CMIP6, which also show a decline in FAVES under future climate change scenarios.
So both the models and the real-world data point towards a weakening AOC and a potential tipping point. But how reliable are these early warning signals? The study mentions comparisons with other indicators.
The researchers compared the FAVES signal with more traditional statistical indicators that have been used to assess AMO stability in the past.
These traditional indicators often rely on analyzing patterns in sea surface temperatures, right?
Exactly, things like increasing variance and autocorrelation in temperature data.
But the study found that these traditional indicators were less reliable than FAVES when applied to the CESM simulations.
Yes, FAVES with its strong physical basis appears to be a more robust indicator of AMO stability than these traditional statistical methods.
So FAVES might be a better early warning system for potential AMOC changes.
It provides a more direct link to the physical processes that govern AMOC stability.
This research presents a compelling case for the AMOC being on a tipping course, but it also acknowledges the need for further research and monitoring.
Absolutely, there are still uncertainties surrounding the exact timing and magnitude of potential AMO changes.
And continued observations are crucial for refining our understanding of this complex system.
Yes, the study emphasized the importance of sustained monitoring efforts like the SAMMA array, which collects data on ocean currents and properties in the South Atlantic where FAVES is measured.
These long-term observations will help us track the evolution of the AMOC and improve our ability to predict its future behavior.
And continued advancements in climate modeling are also essential.
So we can better simulate the complex interactions between the AMOC and other components of the Earth system.
Exactly. Improved models combined with ongoing monitoring will provide a clearer picture of the potential risks associated with AMOC changes.
And this knowledge is crucial for informing effective policy and adaptation strategies to address this looming challenge.
This research on the AMOC has significant implications that go beyond the science itself. It really emphasizes the urgency for policymakers and global leaders to start thinking about the potential societal and economic consequences of a slowdown or collapse.
We've talked about the potential climate impacts, but how would a weakened AMOC actually affect people's lives?
Well, a major cooling in Europe, like the models predict, would have huge effects on things like agriculture, energy demands, and even infrastructure.
It's hard to even imagine Europe that cold.
It would be a dramatic shift. Crop yields could decline, heating needs would skyrocket, and transportation systems could be crippled by extreme weather events.
That sounds like a recipe for economic and social turmoil.
Exactly. These changes would put immense pressure on European economies and could easily lead to social unrest.
And then there are the ripple effects beyond Europe. We talked about this shift in the intertropical convergence zone and how it could disrupt rainfall patterns in vital regions like the Amazon basin and parts of Africa. What would that mean for food security and global stability?
Changes in rainfall patterns can lead to all sorts of problems: droughts, floods, unpredictable harvests. It's a recipe for instability.
And when food production is disrupted, people suffer.
Absolutely. It exacerbates existing inequalities, can trigger mass migrations, and even contribute to political instability in vulnerable regions.
It's a stark reminder of how interconnected our world is. Disruptions in one place can have far-reaching consequences.
Exactly. And this research really drives home the need for proactive measures to both mitigate the risks and adapt to a changing climate.
So what can be done? What are some key steps that policymakers and individuals can take to address this challenge?
The most critical step is to drastically reduce greenhouse gas emissions. That's the root cause of climate change and the melting glaciers that are driving this freshwater forcing.
We need to transition away from fossil fuels as quickly as possible.
Absolutely. Investing in renewable energy, improving energy efficiency, and adopting sustainable land management practices are all crucial.
It's a massive undertaking, and it requires a global effort. No single nation can tackle this alone.
You're right. International collaboration is essential. Agreements like the Paris Agreement provide a framework for collective action, but we need stronger commitments and tangible steps towards implementation.
And sharing knowledge, resources, and technology, especially with developing countries, is vital.
Absolutely. It's about working together to find solutions and support each other in this transition.
Beyond those big picture international efforts, what can individuals do to contribute to mitigating climate change?
Individual actions may seem small, but collectively they can make a huge difference.
Every little bit helps.
Exactly. Things like using public transportation, reducing energy consumption, choosing sustainable products, and supporting businesses that prioritize environmental responsibility all contribute to a larger movement towards a more sustainable future.
This deep dive into the AMOC has been a journey through complex scientific research and its potential consequences for humanity. It's definitely given us all a lot to think about.
It's a wake-up call, but it also empowers us with knowledge and a call to action. The fate of the AMOC and indeed the entire global climate system is intertwined with our choices and actions.
We can't just sit back and wait for someone else to fix this. We all have a role to play.
By understanding the risks supporting scientific advancements, advocating for policy changes, and making conscious choices in our daily lives, we can collectively work towards a more resilient and sustainable future.
It's a challenge, but it's one we need to face head-on for our sake and for the sake of future generations. Thank you for joining us for this deep dive into the EAMOC and its potential tipping point.